Index refraction and the wave aspects of light. The simplest model of light is the ray model. However, the ray model has trouble when you start to look at how it interacts with the medium. In order to answer these questions, we have to talk about the wave model of light. There are three things that we want to talk about. The first one is the dispersion relationship. This says that the index of refraction depends on the frequency of the incident light. So we write the index of refraction as a function of frequency. I'll show you this using an applet. What you're seeing here is that I have a beam of white light. White light is composed of all of the colors of the visible spectrum. So as light comes in, it is going to refract across this glass. And what you're seeing here down at the end is that you get the spreading of these colors. The fact that blue and violet are refracted more tells us that the index of refraction for blue is different than red. In fact, the index of refraction for blue, because it interacts more with the glass, has a higher index of refraction, whereas red interacts less electrically and therefore has a lower index of refraction. That is dispersion, and the ray model of light cannot talk about that. The second thing that I want to talk about is I want to talk about the frequency and the wavelength of light. The frequency f of a wave does not change when light passes across an optical boundary. What this means is that the number of wave cycles arriving per unit time must equal the number of waves leaving per unit time. This statement is actually about a statement of conservation of energy, saying that waves cannot be created or destroyed at the boundary surface. That is, we write the number of waves entering a medium equals the number of waves exiting a medium. This statement is a statement of conservation of energy. Let's explain why this is a statement of conservation of energy. Let's take a glass-air interface and light is passing through it. What you're seeing here is that here in red, this is not the wavelength of light, but it's a time picture. So what I'm actually doing here is that I'm counting how often in time these are going up. Remember that the frequency is 1 over the period, that is from the time from one crest to the next here. The only way waves can be destroyed is if they go through destructive interference. You should remember this from Physics 4A. So that means then, if waves cannot be destroyed at the boundary, then the number of waves passing through must equal the number of waves exiting across that boundary. Therefore, the number of waves going in equals the waves going out. The frequency does not change when crossing an optical boundary. The fundamental thing of light is not wavelength, but frequency. But energy of light is proportional to frequency, and that is also proportional to the apparent speed of light in that medium as well as its wavelength. Since this is so important, I'm going to say it again. Energy of light is fundamental, not frequency or wavelength. But energy of light is proportional to frequency. So it is customary to talk about the energy of light in terms of frequency, but not wavelength. In the language of conservation of energy, we can then write what is the energy of the light wave beforehand, what is the energy of the light wave afterwards, and think about that in terms of the apparent speed of light as well as its wavelength. Since frequency is equal to the speed of light divided by the wavelength, we can rewrite this as follows. In vacuum, which I've labeled with the naught here, the F naught will equal the speed of light, c, divided by the wavelength in the vacuum. However, in a medium, the apparent speed of light and the wavelength are dictated by the symbol n. Let's now apply this to an optical boundary. According to conservation of energy, we know that the energy of N1 and the energy of N2 of the light must be the same. Since the energies are the same, we know that in vacuum, the speed of light is faster than the apparent speed in a non-vacuum situation. In other words, we write the following thing. In order to keep the frequency constant or the energy constant, it's the ratio of the speed of light divided by the wavelength that has to be the constant. So if this speed is higher, then in the medium 2, that speed must be smaller. And as a consequence, to keep that constant, the wavelength of light in medium N1, which is faster, must be longer, and the wavelength in medium 2 must be shorter. We can see this when we look at an applet. If I look at this refraction, if I have a ray that comes in and interacts with the medium right here, we could see here that this doesn't tell me anything about the wavelength or the frequency. In order to see that, I need to then come in and start looking at waves. So what you're seeing here, as this wave is coming in, right at the surface, you see that bending that goes on. And this is very similar to a Larmor example here. So if I compare the speed of light here, note that that speed is moving at the speed of light because I'm dealing with the index of air. However, when I go down to a higher index of refraction, you can see here that by comparison, the wave speed is slower. But at the same time, you could see the difference in the wavelength. You could see that the wavelength here is long, the wavelength here is short. So in order to keep the energy, the number of waves crossing the boundary right here, to be the same, this means here that faster apparent speeds of light have longer wavelengths. When they're at a higher index of refraction, you get smaller wavelengths. So in summary, the important ratio is that for the frequency, regardless of the medium, to remain to be the same, then it's the speed, the apparent speed of light, over the wavelength in that refractive index that must remain a constant. And that leads us to the next and final piece. The wavelength lambda n of a wave is different for different optical mediums. Using the previous fact about frequency, we can write a relationship between the wavelength in a medium and its index of refraction. Starting with frequency equal to a constant, I could use the relationship of wave speed equals wavelength times frequency, and I can rewrite this so that the frequency, which is a constant, should equal the speed of light in vacuum over its wavelength in vacuum must equal the apparent speed of light in the medium divided by its wavelength in the medium. I can further rewrite this using the definition of the index of refraction. If I rearrange this relationship for lambda n, I then get that this wavelength in the index is equal to the wavelength in the vacuum divided by the index of refraction. That is, now that I have that the wavelength in the index is equal to the wavelength in the vacuum divided by the index of refraction, we can now interpret what it means in terms of the index of refraction and the wave speed. We find that if we have higher index of refraction, big N, that the wave speed, which is the speed of light in vacuum divided by a large N, will give me a smaller apparent wave speed, which also indicates that I'm going to have shorter wavelengths. On the other hand, if I have a smaller index n, then I have a smaller index divided into c, which gives me a higher apparent speed and therefore longer waves. Physically, this makes sense for the following reasons. The waves get squeezed, that is, that the wavelengths get shorter. If the wave speed decreases, then that means that the wave is covering a shorter distance per unit time. On the other hand, as the wave gets stretched, in other words, longer waves, then the wave speed must increase since it's covering more distance per unit time. Picture-wise, this is what I draw. That is, for short waves, this peak-to-peak distance represents both time and space. The time is the same for all waves because of the frequency. However, this delta x implies that if I have short waves, they cover less distance. But less distance means that the shorter waves have a lower apparent speed. Now let's look at the long waves here. Long waves, when I look at peak to peak, have higher speeds for the following reason. The time is the same for both of these waves, but longer waves cover more distance. Therefore, longer waves have a higher apparent speed. Now we do our next example, 34.4. Example 34.4. A narrow beam of white light strikes one face of a slab of silicate flint glass. The light is traveling parallel to the two adjoining faces, as shown in the figure. For the transmitted light inside the glass, through what angle is the portion of the visible spectrum between 400 and 700 nanometers dispersed? Because of the dispersion of light, we expect that white light, as it enters the glass, is going to be spread out into its colors. Violet being refracted the most, red being refracted the less. Let's draw this in an image. Following the white light coming in, we could see that once it hits the surface, we have to pay attention to the normal. Relative to the normal, we have the unrefracted line of light, but then violet is going to be refracted the most, red is going to be refracted the less. It is this difference in angle that we're actually trying to calculate. So this angle difference is given by delta theta is going to be theta of red minus theta of violet, since red has a bigger angle relative to the normal. Using the image to the right, we need to determine the index of refraction for violet and red light. We can see here that at 400 nanometers for silicon flint glass, the index of refraction is right here. On the other hand, for red light, the index of refraction is right there. So if we write down these numbers, these are the estimates. Now that we have these index of refractions for each of these colors, we could now go on and calculate the individual angles. However, to calculate these angles, I need to know what the angle that's incident onto the glass. So the first thing that you know here is that if I look at the normal, I know that the normal and the glass here have an angle of 90 degrees right here. This means here that if this is 90 and this is 55, then this angle here must be 55 degrees. As a consequence, if this angle is 55 degrees and these two lines are parallel and with the same normal, then that means that the incident angle of white light is at 35 degrees. Now that I have the incident angle, I could now go in and determine each of these using Snell's law of refraction. Focusing on violet first, I know that light is coming in from air, and then I have the sine of 35 as the incident angle, which is equal to the index of refraction of violet times sine of theta violet. Solving for theta violet, I'm then going to get an angle of 20.2 degrees. Now I'm going to repeat the same thing for the red. The angle of refraction for red is then 20.7. Finally, we could calculate the spread between the beam, which is 20.7 minus 20.2 degrees equals 0.5 degrees. That's the spread between the violet and the red inside the glass.